Good evening, everybody. Can you hear me okay? Let's see, we have Fang, Karen, Mega, welcome. Hope you had a great weekend. Can you see the desktop all right? Very good. Okay, before I start, are there any questions? Well, I don't have midterms. I have tests, like test 1, 2, 3. I don't believe it's on any of the tests. Hey, you're welcome. Yeah, I put that in because of the CC Confer question last week. You need that concept if you're doing multi-programming, because what you want to try to avoid is context switching. So if there really isn't anything else to run, you really don't want to context switch out and then put that guy right back in. And when we get to memory, you'll see why. Let's see. We didn't quite finish Chapter 6. I thought we did, but we didn't. So I wanted to finish Chapter 6. We never really talked about atomic transactions. And there was a question, I believe, on the Chapter 6 homework. But I think everybody got it correct. But I wanted to make sure we went through it. So it basically assures that operations happen as a single logical unit of work in its entirety, or it doesn't happen at all. And it's kind of related to a field of database systems, but it's also related to file management concepts on your disk device. So let's look at a transaction. It's a collection of instructions that performs a single logical function. Here we're concerned with changes to stable storage or disk. So transaction is a series of read and write operations terminated by a commit or abort. Aborted must be rolled back to any changes it performed. And I'll take you through an example of that. Hi Albert, hi Daniel. I think I said hi to everybody else. But that's the concept. And the type of storage media you have is you have volatile storage. And that's like your main memory would be an example of volatile storage. And it doesn't survive system crashes. When you shut your machine down, your primary memory is usually gone. Cache could be part of the motherboard, and that's gone. So those things get removed. Non-volatile storage, disk, tape. Also, there is your ROM, read-only programmable, or EEPROM, electronically erasable programmed memory, EEPROM. Then there's stable storage, which the information is never lost. Not actually possible, so approximates it. We're going to talk about RAID devices as an example of that. But the goal is to ensure that the logical transaction either completes or doesn't, especially when you're in volatile storage. That's part of the issue here. So one base is log-based recovery, is to store the information about a modification by a transaction. Most common is the write-ahead logging. So you have the transaction name, the data item that you're dealing with, the old value, the new value. And then you start the log when the transaction T starts, and then you commit it when this thing hits the commit mark. I think, Windows uses commit type logics for its recovery. So it's used in most of the file management systems, these concepts. They really came from working with databases over the years. That you have a recovery concept that comes in, looks at the log, sees if there's some kind of an error, then it'll undo those. Or it could do redo values in the transaction and then allows it to complete, something like that. Really tough to do recovery stuff. If you've ever written any programs that you try to restart, let's say a payroll program, try to restart the payroll program. Something like that would be kind of difficult to restart. Because some checks were written, some checks weren't written. So you either figure out where you left off and continue writing the next set of checks, or you throw out all those checks and restart the whole check process. Checkpoints is what's the terminology used to say that something has been logged. When you're dealing with multiple transactions, you've got to somehow serialize them so that you get them correct. For example, this is a good spot to come to the example. You have two sessions running. They're running concurrently. So you have a session ID like 100 and 110. Well, each event is going to occur at a certain timestamp, and then 100, there's 100 timestamp, and it issues a begin transaction, and then you get the second session at timestamp 105, and it does a begin transaction. Then 100 at time 110 updates a record, and the before change image is stored. Okay. 100 at 115 deletes a record. The before delete image is saved. Then 110 at 120 adds a record. So you save the position and location of that add, so you know what was added. So there's usually a pointer or something saved. And then now back to 100, 125 updates a record, and the before change image gets saved. Okay, and the system goes down. There's a failure. The hard disk or whatever this is writing to fails. So the restart of the database looks at the log, sees there's no commit, that there's a begin. So it's reading through this transaction log and sees a begin, but sees no commit at the end. So it takes and restores the before image for this session. Okay. It deletes the location 110 add, deletes that location for 110 session. For the 100 session, it adds that image back because it was deleted. Let me think, was it deleted? 100, where's the next one that does? Oh, it restores that image, the before image, before the delete here. 100 deleted. It adds that saved image. And then restores the image before the change. 100 restore commit ends. 110 restore commit ends. So now it self-committed and it rolled back all of these changes. That's really what happened. It rolled back this update. It added the record that was deleted. It deleted the record that was added, and it modified this record to the before image. And those were the steps it did right here. And it ends up with its own little commit. Now what happens is that transaction would have to get restarted, and then at the end of it, if it actually goes through all of it, it would issue a commit. And that's the way these database transaction logs work, as well as file system recovery logs work. It's all based on this logical record concept. Any questions on that? Okay. There's a concept that I probably will talk about when we talk about files, but it comes to mind right here, is there's something called raw files that if you were, in programming, you could write directly in Unix to the file itself without going through the Unix file system. They're called raw files. And in this case, you have to maintain your own buffering and recovery. The OS file system has buffers in memory. So if it fails, it may not be able to recover that file system. And if you are in a Unix world, now this is probably file system type in Linux. The file system type 3 has a logging mechanism. But if you were in a prior to that kind of file system, before you shut the machine down, you would do sync. And what that does is it flushes all of the system's file system's buffers back to disk. That's the purpose of sync. And then you could issue the shutdown. I remember doing this back in the mid to late 1990s on a Sun box when we had to shut it down. You would want to go through this process. We had the Informix database on that system. And then there was also Sybase, which was created in Berkeley, and Microsoft licensed it, and it's called SQL Server today. Sybase, I think, is pretty much gone as a company, maybe because of Microsoft. But they had a good system. Okay, this kind of event is a log file event. These events are things that you would do on a database. I just threw them in just to show you kind of the different locking mechanisms that programmers tend to use. One is the whole database. You lock it. You're going to do a complete big update. no user is online to that database, it's easier just to lock the whole database, because once it's locked, you don't have to worry about all the little locks that go on. But if you can't lock the whole database, the next level is you lock a page, because we're talking about a relational database, and relational databases use pages, so you could lock the page that the record is on. The database does this for you. Or you could lock the individual record on a page. This is more complex, and this is where you would get into deadlocks, right in here, where you lock either pages or records, and we're going to show how that works in Chapter 7. And then the last concept of locks is, when is the lock set? If you lock on read, it's a pessimistic lock. If you lock on write, it's an optimistic lock. And that's about all I'm going to say on this one. We might come back to it after we talk about deadlocks. Any questions on this concept of logical atomic transactions? It's a similar concept to what we talked about, that machine instruction. Tested set, test reads a value, sets a value without getting interrupted. Well, these things could be interrupted because you see session 100 and session 110 are running throughout the timestamp, right? And other sessions are running as well, but they're in between all this stuff. So what you're trying to accomplish is the whole transaction goes or none of the transaction goes. And if you kind of think about it, a simple case is you go to an ATM, right, and you ask for money out. Well, it goes to your account, right, your bank account. It deducts the amount, right, and let's say you don't get your money. It never pops out of the machine. Well, the transaction never completed, but it took out that money from your account. Well, you don't want that, so it should back that back out and give you that money back into your account. Okay, that's one way of doing it. The other way, it's even worse. Listen to the other way. I'm thinking now from the bank's perspective. The bank gives you the money you want, and then it has a failure of updating the transaction in the database. Well, you've already got your money. You're happy as a lamb because it didn't deduct. Well, they're not going to like that either. So they would do some sort of a start transaction, give you the money, and then if you it fails, when it comes back up, it would have had that transaction recorded somewhere so that it would deduct from your account. Any questions on that? How you guys doing out there? Okay. Good. Good. Yeah, it's just showing you the same thing I was showing you about these events and what's happening with them. And then you have this non-serial schedule, which is a lot more complicated. Okay, a lot more complicated. I talked about the locking mechanisms. Each transaction issues locks and unlocks in 2 phases. One is growing, obtaining, and one is shrinking, releasing locks. As long as you manage these transactions, you can prevent deadlock in this mechanism. There's other ways where you can't. Timestamp ordering, that's kind of what I was showing you as an example. I'm not going to spend a lot of time on this because we're going to talk more about it in file management stuff. So you're not going to see this kind of stuff on the test. Okay? So you don't have to worry too much about that. I just want you to understand the concept of what it means. Okay? What atomic transactions mean. It's a mechanism to recover in case a failure occurs. So it's that all or nothing, and I think it was a question on Chapter 6, so that you could pick up that knowledge. Okay, good. I finished the monitor example with you, but I want to make sure that you understand it. I will review it again on Thursday. I'm going to review all of this stuff that we went over. Were there any questions on this monitor and how to answer these questions? I don't see any, so we're pretty much done with this thing. Like I said, I'll review all of this on Thursday. Okay, 7, it is a cool chapter. 7, the multi-level feedback cube, yeah, I'll do that on Thursday, okay? But I need to spend some time on Chapter 7 with you guys, because there's a bit of material in here that's of high interest. This is kind of like the what could happen in a multi-programming environment when you're issuing resources to processes and they still want more. That's kind of what this chapter is about. So let's take a look at it. The deadlock problem. We'll look at that. We'll look at the system model. Okay. It's a set of events which prevent a set of concurrent processes from completing their tasks. Okay, so what we look at is how do you prevent a deadlock? If you can't prevent it, how can you avoid a deadlock? If you can't avoid it, how can you detect a deadlock? And then what to do if you do detect it. That's the steps that we're going to take in this chapter. So prevent, avoid, detect. So what is a deadlock? This is probably a good example of a deadlock. You have a one-way street. Only one car can get through this bridge, let's say. And this car is kind of stuck. Now you can't back up. Let's assume it can't back up because this car is in its way. This car here can't back up because this car is in its way. So it's stuck. And each direction is a resource. So this bridge here that we've got is a resource, and it's bidirectional, meaning we can go in both directions, but only one can get across at a time. And if you are deadlocked, like this situation here, you have to figure out what to do to get out of that situation. Please note the bottom note. Most OSs do not prevent or deal with deadlocks. And you'll see why. I mean, this is one of the more fascinating items. Here's the process that really, procedure rather than thought. Each process uses a resource as follows. So the procedure is request a resource, use a resource, release a resource. Okay. For example, memory. It requests memory. It needs more memory because it's doing a malloc if you're in C, or you want to request a printer. Okay, and you're usually requesting serial reusable devices like printers, tape drives, disk drives, memory, things that you can use for a short period of time and give up, and then someone else can use that. That's called a serial reusable resource. And these are the 4 steps. I want you to know these 4 steps. You're going to see them on the test. The 4 steps are, first, you have to have mutual exclusion. In other words, only one process at a time can use a resource. All right, this is a key one. Imagine I give memory to process A, and then I give that same memory to process B. What could happen? Well, it would be awful. So mutual exclusion means only one process at a time can use a resource. Hold and wait. A process holds at least one resource, is waiting to acquire additional resources held by other processes. So this is the second requirement for a deadlock, is hold and wait. No preemption. Okay, now this is where remember I talked about non-preemptive operating system versus preemptive? I don't want you to confuse it with this concept. This no preemption applies to a resource. A resource can only be released voluntarily by the process holding it, after that process has completed its task. In other words, when it requests a resource and the operating system gives it, it can't arbitrarily take that resource away while the process is still needing it. That's what this means. It's like I'm writing a backup to a tape drive, right? I'm writing a backup database to a tape drive. And I'm writing it, and I'm writing it, and I'm writing it, and all of a sudden the operating system says, I'm going to preempt you from that resource. I'm not writing it anymore. I don't know what I'm doing. I don't have my tape there. And I have to either restart the whole thing or figure out how to restart from a certain location. Well, that's kind of silly, and that's why you don't want to preempt. So that's this rule. And finally, there's this concept of circular wait. So if it's waiting for something, it would be something like this. P1, process 1, is waiting for a resource held by process 2. Process 2 is waiting for a resource held by process 1. That's a circular wait. Or you could do it this way. Process A is holding a resource needed by process B. Process B is holding a resource needed by process C. Process C is holding a resource needed by process A. It's a circular wait list, and that's what this is all about. Okay? Those are the 4 conditions. If you don't have one of them, you might be able to prevent deadlocks. And that's the next topic. Make sure that that's the next topic. I'm going to come back to resource allocation graph. Okay. I'm going to use it differently. So I'm going to come back to this concept. Well, this might be a good way to look at it. Okay, so I've got a resource and I've got processes. And the way to interpret it is I've got one resource of resource 1 type. I got one of resource 3 type. I've got 2 of resource 2 type, and I've got 3 of resource 4 type. That's how you kind of read this diagram. And I have 3 processes. P2 has this one resource. That's what it means. Is R1 is owned by P2. P2 wants, that's what this arrow means, P2 wants an R3 resource. It just happens to be held by P3. P3 wants one of these, and each of those are held by P1 and P2. So you've got resources holding, you have processes holding resources. Like this one's holding that one. This one's holding that one. P2 is holding basically 2 of them and wants another. P3 is holding this one and wants one of these. This is a deadlock. They will never, ever complete. So remember the 4 things required for a deadlock. I can't arbitrarily preempt this resource from P3 to give it to P2. I can't do that. Mutual exclusion. I can't give our resource 3 to both P2 and P3 at the same time. So that's mutual exclusion. I can't do that. I can't preempt. I'm holding a resource while waiting for another, so that's hold and wait. And finally, there's a circular wait concept going on here. And that is the definition of deadlock. That's an illustration, classic, of a deadlock. Here they're showing one with no deadlock. Okay, well, why is it no deadlock? Because P4 doesn't need anything. Therefore, it will eventually release this resource. P3 can get it and release this resource. P1 can get that and release this resource. So, it's not a deadlock. Okay, I'm going to give you my own definition of that. Okay, these are some methods for handling, right? Ensure that the system will never enter a deadlock. That's called prevention. Allow the system to enter a deadlock state and then recover. Ignore the problem, pretend that deadlocks never occur. And this is most used systems, including Unix. Yeah, Windows does the same thing. Okay, so our first look at this is, well, let's see how we can prevent deadlocks. So basically, restrain the ways a request can be made. Mutual exclusion, not required for shareable resources, must hold for non-shareable resources. Okay, so you could break them up into shareable versus non-shareable. Hold and wait. Must guarantee that whenever a process requests a resource, it doesn't hold any other resources. Back on the mainframe many years ago, when I started programming on the mainframe in the 1970s, you had to pre-allocate all the resources to the program before it ran, and that's how it avoided this deadlocks from occurring. But you could somehow eliminate no preemption. Well, you can't do that. You could do this concept of a list of resources. You can maybe list all the resources and prioritize them and do that kind of stuff. But as you'll see, that these concepts were tried and rejected. So I don't want to spend a lot of time on them. They're not fun. This is where it starts to get fun. Okay, I want to look at a way to avoid deadlocks. The simplest and most useful model requires that each process declare a maximum number of resources of each type that it may need. So the deadlock avoidance algorithm dynamically examines the resource allocation state to ensure that there can never be a circular wait condition. The resource allocation state is defined by the number of available and allocated resources and the maximum demands of the processes. So we're going to look at this in a little more depth. So there's a concept called a safe state. And the definition is, its system is in a safe state if there exists a sequence, whatever that sequence is, of all the processes, the system such that the resources can still request and be satisfied by the current available resources. So it's kind of hard to understand it in these words. You'll see the example and I think you'll understand it better. So it basically says if PI resource needs are not immediately available, then PI can wait until PJ have finished. So there's a wait kind of concept here, that until another resource until another resource releases what the other process needs, it can sit and wait. But the idea is that there is always a path for all processes to finally complete. All right? So, if a system is in a safe state, it guarantees there's no deadlocks. Okay? If a system is in an unsafe state, it doesn't mean it's deadlocked. It means there might be a possibility of deadlock. So if you're trying to stay in a safe state, what you do is you run your algorithm, your avoidance algorithm, to see if an allocation request is going to move you from the safe state to the unsafe state. If it is, you don't honor that allocation. So you stay in a safe state. And that process would just have to wait, be in the wait state, waiting until another process releases the resource that it was trying to allocate. And that's the definition of avoidance. Ensure the system will never enter an unsafe state. And here's a good visual look at it. Okay, if you're in a safe state, you're not deadlocked. But if you move to an unsafe state, you may or may not be deadlocked. Okay? I think I have a question on there somewhere on this. Before I leave this, does this make sense to you guys? Okay. So there's avoidance algorithms. I'm going to use resource allocation graph a different way. So I'm not going to use it in avoidance. Okay, I'm going to kind of skip over this. And the reason I'm skipping over this is I want to use it for detection, not for avoidance. The book has good examples of how this works. You want to know, I'm not going to ask you in detail how all these things work, okay? I am going to illustrate this stuff with an example, and we'll do that in a minute. It's nice to go, if you wanted to go through this algorithm, it's a pretty good algorithm to see how it really works, but it's not required by me. Let me show you what is required. You have this on, you have this concept, and this file is on Canvas. And this is what it's going to look like on the test. So it's going to be a multiple choice question. It's worth 3. And the answers would be A, B, C, D, or E. So let me show you how it works. You have 4 processes, and there's 5 states of the process. Each one of these is a state. We don't know if the state is safe or unsafe, but we want to say which state is unsafe. So 4 of them must be safe, and 1 of them is unsafe. So let's see if A is safe. And here's how we would do it. For process 1, it needs 2 of these resources. First, we have a total of 12. We're only doing 1 resource, which makes this really easy. We have 12, let's call them printers, I don't care. There's 12 of them. Process 1 needs 2, process 2 needs 6, process 3 needs 5, process 4 needs 7. They currently have this number. They have, process 1 has 1, process 2 has 4, process 3 has 2 of them, process 4 has 4 of them. So if you added up that, there'd be 11 that are allocated, and there's 1 available. Okay? Now, what you would do is say, okay, can a process get all of its needed resources and complete? And you want to do that for each process. So basically, number 1, if process 1 needed another one, it could have one. It's right here. Now this would be 0, this would be 2, and if it finishes, which it would at some point, it would release those 2. So now I would have 2 available, and 1 is gone. I can take these 2 and give it to 4, okay? And 4 would get it 6 and release the 6, so now I have 6 available, and I could take 3 of those 6 and give it to 3, and it would have its 5, and it would go away, and now I would have 8 available, and if it needed 3, I could give them 3, and therefore all of these could complete. Therefore, this is a safe state. Let me show you when it would not be safe, okay? Let's assume that this is the setup, and process 2 wants a resource. I have one. If I give it to 2, I would have 5 here and 0 left. And if process 1 needed another one, I wouldn't have one for it to finish. If the 5 here needed another one, I wouldn't have one. If this one needed one, I wouldn't have one. If this one needed one, I wouldn't have one. If I gave the 1 to process 2, I would have an unsafe state because they wouldn't be able to finish. Therefore, I would not allocate this to process 2. But I could allocate it to process 1 and meet its need. Okay, does that make sense to you guys? Okay, any confusion? No, if process 2 needed 1, you mean needed 1 here, maximum need? Is that what you mean? Oh, if 5 were a maximum need, yeah, then it would still be safe to give it to 2. That's correct. So it would be safe to give the 1 to process 1, and if this was a 5, give it to process 2, and this state would still be safe. That is correct. But the way it's set up, the only process that could really get 1 is process 1. I cannot give it to 2, 3, or 4. If I did, I would be in an unsafe state because none of them would finish. And the other thing I need to say about this is the maximum need doesn't know, we don't know if it's already had its maximum. We're looking at a current point in time. Process 2 could have already had its 6 and is now giving them back. But we can't predict what a process is going to do. So a process might hit an if statement that says, oh, I need more of the resource. So it's going to go back to get the 6. All right, so you got that thing going on too. All right, so that's A. We know A is safe. And the only one in this environment that we could give it to would be process 1. And then once we gave it to 1, we know it would finish. Then we'd give it to 2. We know it would finish. We'd give whatever's remaining to 3, and then to 4. That's how we know that it's safe. I can complete all of the requests. Okay, let's look at B. I've got 2 available. Process 1 has 1, needs 5. Process 2 has 2, needs 4. Process 3 has 3 and needs 6. And process 4 has 4 and needs 7. Okay. So I could give the 2 to which process to allow it to complete? Which one? Yes. I could give it to 2, giving me 4, and then 4 would complete, and I could take those 4 and give it to process 1. It would complete, and I would now have 5, and I could give 3 here, and it would complete, and then finally I could give 3 here, and it would complete. This is a safe state. Okay, let's try C. I have 1 available. Process 1 has 3, needs 4. Yeah, the only one that could be allowed to get this would be process 1. That's right, to be able to complete. Then, which one would get it? Let's say this guy's done and I have 4 available. Could I give any of them to 2 or 3? No, I have to give it to process 4, you're right. The only one that would complete and give me enough to complete these guys. That's right, you guys are getting it. Anybody not seeing that? Just tell me if you can't see it. All right, let's do D. I have 0 available. 1 has 4, needs 10. 2 has 4, needs 8. 3 has 0, needs 4. And 4 has 4 and needs 4. Process 4 will finish and could give it to 3 or give it to 2. They would finish. If it gave it to, those 4 were given to process 3 and it finished, I could give the 4 to process 2. I cannot give it to process 4. Process 1. I could give the 4 here. That's correct. So this is a safe state. Well, by elimination, this must be the unsafe state. Well, let's find out. Yeah, well, I've got 1 available. Process 1 has 8, needs 12. Process 2 has 0, needs 3. Process 3 has 2 and needs 4. Process 4 has 1 and needs 4. If I give 1 to any of these, It'll never be enough to get them, all of them. Therefore, this is an unsafe state. You see how this works? So the algorithms that he's talking about would determine that a safe state, if I granted the allocation, so what it's doing is a what if. The algorithm is a what if. What if I give the requester process that resource? Will I still be safe? If I'm not safe, I won't give that process that resource. That's the summation of this concept of avoidance. And it works. And there were, I don't think there are anymore, but there were operating systems using this concept. And we'll talk about some issues with this. But do you understand this question and how you're going to see it on the test? Is that a yes? Okay, thanks. Yeah, I'll review this again. I'm going to review all these little diagrams later on Thursday. So this safety algorithm is the algorithm that checks for safe state. Okay, and it's pretty cool. And you can see an example here. It's more complex than my example. Not sure if I have a problem on your chapter 7. I can't remember if one of these is on the homework or not. Okay, so before we leave avoidance, though, I need to just ask a question of you guys. Okay. When do I run this safety algorithm? Okay, but when? What triggers me to run the algorithm? No. Good guesses. Karen and Mega, those are great guesses. What would trigger me to run the algorithm to see if I'm going to move from a safe to an unsafe state? What would be the event that would cause me to go from a safe to an unsafe state? Yeah, that's true, but that's not the... Yes, Karen, you got the word in there. I don't know about concurrent, but requests a resource. When a process requests a resource, I need to run the checker, the safety checker. Now think about that. How often is this sucker going to run? I mean, how often do programs request resources? All the time. All the time. I mean, all kinds of resources. So it's going to be running quite often. And of course, when it's running, right, when it's running, you're not running any real user programs. You're running the operating system to try and avoid a deadlock. So why I'm telling you that is there was an attempt to implement this in the 1980s on a mini computer, and you had to specify as a programmer the maximum number of resources that your program is going to need for all the resource types. Well, think about programmers. First of all, they're good, but you know, are they that good that they're going to be able to figure out that your program is going to need that many resources? So there's a lot of problems with this. The problem is, you know, you've got to know all the types. You've got to know the maximum each one's going to require. You have to feed that into your operating system when you request the program. You have to, the program has to run on every allocation request. It's got to run this to see. And this algorithm is not a simple algorithm. It's going to take some time. So all of those things really cause us to forget avoidance. Okay? Let the deadlock happen and detect it. Okay? So you allow the system to enter a deadlock state. So we're not going to prevent, we're not going to avoid, we're going to let it happen and try to detect it. Because you don't know if it's really happened or not until the system starts really slowing down and things aren't going through it like at a normal throughput rate. So you've got to be able to detect that something, it just may be slow, it may not be deadlocked, it just may be slow. So you've got to have a detection algorithm. So let's take a look at that. So you maintain a wait for graph. Periodically invoke an algorithm that searches for a cycle in the graph. If there is a cycle, there exists a deadlock. Okay? An algorithm to detect the cycle in a graph requires an order of n squared operations, where n is the number of vertices in the graph. This could get quite cumbersome. Okay? So let's look at a resource allocation, right, and the corresponding wait for graph. I'm going to use the resource allocation, and I'm going to give you my own algorithm, okay? And that's this one. And it's also on Canvas. So here's the idea. You know, we'll have our own algorithm. And the algorithm's really simple. First, let's look at the diagram. I'm using circles to indicate resource type and squares or boxes to represent processes. It's just the way I started this. It's kind of different than the way the book is, but you get the idea. And when I have a resource owned by a process, that's what this arrow represents. When I have a process wanting a resource type, I have an arrow going to that type. Works the same way. So here's this complex environment. I've got 5 processes and 4 resource types and a different number of resources in each type. Is that clear to everybody, how the diagram works? Yes, good. Okay, the rules are real simple. If a process has all of its resource, reduce it. All right? In other words, remove it off the chart. And that would release any resources it owns. Step 2, if a process needs a resource and it's available, grant the access. And step 3 is go back to step 1. All right. Finally, if there are any directed lines left, then those processes are deadlocked. Otherwise, no deadlock. Okay? So we're going to go through, and you're going to have something on the test that looks like that. So you're going to have to determine if it's deadlocked or not. And then you go through these steps, right? And you can almost pick any one. P1 wants one of these, but they're not available. P3 wants one of these, and there's one available. So, where did I start? Yeah, I said give one R4 to P3. Give one R4 to P3. And now it has everything it needs, and it will finish. And then we can reduce P3. So we let go of this resource, and we let go of R1 type resource. So P3 is gone. You have to keep this, when you do it, you'll have to kind of keep a note or something so that you know that you've already reduced that. When you see it on the test, you can, I don't know how you're going to do it on the test because you're not on paper, but you'll do it as best you can. You can print this and do it on paper if you want. So you reduce P3. So now give one R1 to P1. So now you go back to step. Does P1 have all of it? Yeah, it has. So you can reduce this one. Okay, now you can give a P4, an R2 to P4. I don't know if we do that next. Let's see if we do that. Yeah. Give one R2 to P4 and reduce it. Give one R3 to P2. Give one R3 to P2 because we reduced P4. And now it has all of it. Reduce it. So reduce P2. Give one R2 to P4. Reduce P4. Give one R1 to P5. So R1 to P5. And reduce it. And we're done. Nothing left. It's not deadlocked. I want to stop a second. Is that clear? Sure. Yeah, it's hard to. Let me do this. You can see it all in one chart. When you reduce a process, you free up the resources that it owned. It's a what-if game. You're playing a what-if game in this method. You don't really, in reality, reduce anything. What you're doing is you're seeing if it can be reduced by eliminated. It's a what-if scenario in this algorithm. So reduce it means remove it from the owning a process or owning a resource. Here, let me try a different tact here. I just spotted this. Let me search. Yeah, columns. Still not giving me what I wanted. me do it this way. I did it in the wrong spot. I want it up here in the column. So let me undo it. I should have done this in 2 columns. I want to do it here. This, I want a second. There. Now we can see it together. There, that better? Well, you start with the first rule. If a process has all its resources, reduce it. Well, I don't have that situation, okay? I don't have a situation where it has all of its resources. So I go to step 2. If a process needs a resource and it's available, well, this is unavailable, unavailable. Ah, this one's available and P3 needs it. So I would grant it. That's what this would mean. So P3 would have gotten this resource. That's how you know where to start. You have to look around the chart to find out, first, is there a process that has all of its resources and can be reduced? Second, if that's not true, then if a process can access a resource, grant it, give it to it, and then reduce it, which would free up these guys. Owned by P3 would free up those 2. Then you go back up. If it has all its resources, reduce it. If it can obtain one, grant it. It has all of its resources, so it could complete, right? It could complete, so we can reduce it, and we keep reducing it, and that's what his algorithm is all about. Here, this algorithm here is about this concept. It's just I'm showing it from this perspective through the rules. I'm not showing it through code. Okay, I'm not doing any of this code here, this detection algorithm code. I'm doing it from a pictorial called graph reduction. This is a graph reduction concept, where you can see it. Okay, so if this was code, and I'm running the algorithm here, if this was code, it would be a what if. And I would start the what if right here. P3 could get this and finish and release these 2. Then what would be next? Well, I could have done P1 instead of P4. It doesn't matter. I could have started with P4 or I could have started with P1 because this was free and this was free. It doesn't matter, the order. If I did this instead of this or this instead of that, it would still come out the same because it's not deadlocked. And eventually what happens is you have no more lines. They've been reduced, and all you have left is 5 processes and the resources listed there. That's what would end up. Because by reducing, what you're really doing is you're reducing the ownership of the resources. You're reducing that line, this line right here. The outgoing lines are being reduced. Maybe that's a better way to say it than the process. These owned lines get reduced, and eventually there's nothing left. And if there's no lines left, then it's not deadlocked. It's not deadlocked. If there are lines left, then you've got a deadlock. Good. Okay. We're not quite done yet. We're moving along pretty well, though. Okay, now here's the next question for you guys. I'm allowing deadlocks to occur. When do I run this algorithm? Mega, that's a good idea, but remember what I said about how often you request resources? And this algorithm is going to take up much more compute time than the previous avoidance algorithm. So I probably would not do it every resource request. Any other thoughts? But Karen, this is the algorithm to run to detect the deadlock. But how do you know when it happens unless you run the deadlock algorithm? Albert, when a new process is added, okay, a new process is added, and maybe there's no processes added for minutes or hours when suspending a deadlock. That doesn't make sense, Kang. It's a good guess. Hi, Steve. Hi, Kang. I missed you coming in. Karen, I don't know if I spotted you already. When suspecting a deadlock, I want you to kind of tell me specifically when would we run the detection algorithm? No, Mega, you don't know when it happens. Right, that's why we let it happen, but how do we know we have a deadlock when we run the algorithm? No, that's not the question I want to ask. The question I want to ask is, what triggers me to run the algorithm? Now you're getting closer, Steve. You're getting closer to the concept. You guys are getting real close to the concept of what I'm trying to lead you to. Take a look at our states. What does it mean to hold and wait? Yeah, Karen, now you're getting on it. You're getting on it. If it's blocked, and it's been blocked for quite a time, no, it wouldn't just be, it would be how long is something blocked? Not all blocked. It's how long a particular set of processes have been blocked. That would trigger the algorithm. That's one mechanism. There's many different mechanisms, okay? First of all, it's going to take time, right, to run your algorithm. So if you have a process that's blocked, you know, waiting for a resource, and there's got to be 2 or 3 of them, maybe, you would run the checker, the algorithm, and then if it determined the processes, let's say it's P1 and P3 are blocked, right? P1 and P3 are blocked. They've been in the queue. P1 is probably be in the queue maybe less than P3 time waiting. So whatever triggers the algorithm, I discover the actual processes that are blocked. That's what's going to end up when I run my algorithm, this algorithm. So one time is if a process has been blocked for quite a while, I mean quite a while, maybe 5 seconds, guys, then I might run the checker. If another operating system might use a different concept. For instance, let's see. Let me go back to that diagram. It might not even look at any of the states, and it might, on a timer, every 10 seconds, run to see if anything's deadlocked. 10 seconds, run to see if anything's deadlocked. 10 seconds, run to see if anything's deadlocked. As part of a timer interrupt. If it's been 10 seconds, run the checker. So any of those mechanisms are good mechanisms to trigger the deadlock detector. You don't want to run it, you know, every time you dispatch. You don't want to run it then. Is that clear? Okay, good. Okay, we're going to move on. That's quite a lot, that matrix. So, like I said, how often is it likely to occur? How many will need to be rolled back? How often? We went through that. Okay, but once we've detected, what do we do? Once we've detected, what do we do? And there's a classical example of a deadlock. Process wants a resource, holds a resource. Process wants a resource, holding a resource, can never, ever get out of this state. It will always be locked. Okay, recovery. Abort all the deadlock processes. That's one way. Abort one process at a time until the deadlock cycle is eliminated. Both of these are used. Depends on the operating system. In which order should we choose to abort? Do we use the priority? See, these are design questions again. There's no right or wrong answer here, guys. It's what you think of when you're developing your system. What kinds of mechanisms are you going to do when you discover a deadlock? How long the process has been computing. For example, remember I talked about a backup of tape. You know, it's backing up your database. It's been running for 2 hours, and you found that it has a tape drive deadlock. You don't want to kill this guy. You want to kill the other one. You don't know this, guys. This is not known. How much longer to completion? You'll never know that. Remember, we talked about this. You don't know the speed of any program. You don't know how long that program is really going to run. You could guess, but you don't know. Not for sure. Resources the processes use. You could base it on that. Remember we talked on the avoidance side. It had need of 6, and maybe it's giving them up. So you could use that. Resource process needs to complete. How many are needed? Once again, you really don't know these things in advance. How many processes will need to be terminated? Well, yeah. And is the process interactive or batch? You might decide on that person. So there's a lot of different ways you might design your operating system. Most of them just pick one and continue. You know, they'll kill a process, check, see if they're still deadlocked, kill another of the deadlocked processes until finally it's no longer deadlocked. That's the way most operating systems work today. Selecting a victim. I like that. Selecting a victim. This concept of rollback, return to some safe state, restart the process for that state. If you've ever done any programming, it's really difficult to do this. Really difficult. To write a program that's restartable at a certain location. So if your program did get killed as a deadlock resource or something, it could restart at the point of which it was killed. Then you have to worry about this. There's always starvation possible, and you may always pick the same process to get rid of, and it may restart, right? The process may restart, and get selected to be killed again, restart, get selected. Do you think this is fun? Concepts? are you getting you liking this idea? These ideas? Yeah, it is fun and funny. Yeah, I really like deadlocks, and that's the end of the chapter. Okay. Questions? I think I went over everything that I was showing you. Yeah, there is. I believe there was. We can take a look at it. I'm going to go over the test more so next time, but I just wanted to review with you the format. Oh, that was off too long. Okay, let's take a look. Chapter 7 question. Okay, there's an unsafe question, so that's an avoidance. Okay, there's a starvation question. There's an example of, you know, the 4 necessary conditions, right? Mutual exclusion, no preemption, hold and wait, and circular list. Those are the 4. Is this the one you were talking about? Hang on, I have to catch up to you. Kang, I have to catch up with you. Let's see. First, is that the one you're talking about? Suppose the system is unsafe. Show it's possible for the process to... Oh, it's the first one. It's not deadlock. It's talking about avoidance concepts. So it's in an unsafe state. Show that it's possible for the process to complete their execution while entering a deadlock state. So I want you to illustrate that. And how you might do that is here. We know this is an unsafe state. You guys agree? Remember we went through this? Okay. Instead of process 1 going up to 12 and needing the 12, it's deallocating, and it's going to release all 8 of them. And from that, this could complete, this could complete, and this could complete. So in that one regard, they're not deadlocked if it so happens that this guy is releasing resources. If it's not, then this may or may not be deadlocked. We don't know. But it could complete, even though it's in an unsafe state. It's possible. We can't tell by this diagram here. We can't tell if it's deadlocked. What we can tell is it's unsafe. But I showed you that there's a mechanism, a way that it could complete and become safe. Did that answer your question? Well, you don't. You're making the assumptions, Mega. You're making the assumption. Because we don't know whether it is going and increasing the number of required resources or it's decreasing. or deallocating the resource. But I know that's one way. I'm thinking about what you're saying, Kang. We assume that the one that can't get resources yet will release and wait. Well, will release and go away. I don't know about wait, but yeah. Yeah, we're assuming in this example that it's an unsafe state, but it may or may not be deadlocked. We don't see it. We don't see it. This doesn't show. That's the whole idea about avoidance. You know for a fact if it's in a safe state, it's not deadlocked. You know for a fact that's the case. When it's in a safe state, it's not deadlocked. But if it's an unsafe state, we don't know if it's really deadlocked or not. So what the question is really trying to ask you is, suppose the system's in an unsafe state, show it's possible for the process to complete their execution without entering a deadlocked state. And I showed you that. I showed you that mechanism in our example. So you could use something like that to illustrate. Did that help? Okay. Yeah, I know it's a little confusing, but this is really a thought question. And just illustrate an example. Take like I did here, take a unsafe state of resources and processes and show how they can complete, therefore they're not deadlocked. We can't tell they're deadlocked here. All we know is they're unsafe. So I picked an example of that. The only way that it could be is that process 1 is releasing resources. The only thing that could make this work. If none of them were releasing resources, or if this guy wasn't releasing, then we can't determine if it's deadlocked. This mechanism that we're using cannot determine deadlock. This method, maybe you could use both of these. Where was that? This method can determine if it's deadlocked. Because what you're doing here is you're actually looking at each of the resources being allocated to each process. So this can actually show if it's deadlocked or not. The avoidance stuff can't. And that's kind of what I was trying to explain, and that's what you would explain to me in this. How can they complete their execution without entering a deadlocked state? So make up an example of an unsafe state and show me the steps that would be taken to complete them, basically. Therefore, they're not deadlocked. If they can reach a completion, all the processes would reach a completion. They can't be deadlocked. This diagram shows that case, that after we did graph reduction, we didn't have any more lines left requesting things. Or arrows left, I guess. Okay. Questions? Okay, let's look at real quick at test 2. I've got 2 tests on just like on test 1. Let's look at Canvas. And I'm going to review all the chapter stuff with you again when we on Thursday. And Thursday should not take a long time. I mean, unless there's lots of questions, we should have it done within I would say an hour or so. I wanted to scroll to, it's taken a while. There you go. So, just like test 1, there's 2 tests. There's the 45 question test required to be done, and there's an optional, if you want to get earn 5 points, there's an optional one. I've given you 2.5 hours to do the first one, and I'm giving you a half hour to do the optional. Okay? So the format is, of the 45 points, 5 true and false questions worth 1 point, 5 multiple choice questions worth 3 points. You already know one of them. This is going to be one of them. I'm going to change the data, but it's going to be the same problem. I might even say which one is safe versus which is unsafe. I don't know. So 5 multiple choice questions worth 3 points each, 5 fill in the blank questions worth 5 points. I need you to note this. For the 5 fill in the blank questions, ensure your window is open large enough to show the answer correctly. So what I mean by that is I've pre-formatted the answer area to make it easier for you to do, like the multi-level feedback cue stuff. Let's see if I can give you an example. We'll preview this. So this area here is what I'm talking about. It'll be a formatted area, and you could copy and paste into from here, from the example here. You can format it, copy and paste in your answer here, but it's not big enough. So what you want to do is you probably want to go full screen on it. Full screen on it, and I forgot how to make it wider. You might want to do view. That might do it. View, zoom in. There we go. Yeah, and that would do it. That'll help you to see it better. Okay, when you answer some of the fill in the blank questions. Is that clear on that? Okay. And I think I've done everything. Let's check. We went through 6. We finished that. We went through 7. That homework for chapter 7 is through the 11th, so that's this Sunday. I finished the monitor example. Thursday we'll review the test. Thursday I'll give the CC confer answer. Review, we did that. Questions? Semaphores. Sure. Okay, suppose we have the idea is you have a CD4. This is the way I think of it. Has 3 components. It's got a request kind of component and a release component and a variable, a counting variable. That's kind of the idea. So let me request, I'll start with my variable. Let's say my variable is the number of CDs. The number of CDs. I have 4 of them. Okay. So process A runs a request on CD numbers. So requesting semicolon. The requesting semicolon. If CD number is less than 0, then wait on. It has 4 components. I forgot to put down wait queue. Associated with it. So it's got a request kind of concept, a release concept, a wait queue, and wait on the CD queue. Okay, else decrement the number. Decrement the number of CDs. Okay? And you would allocate one of them. Okay, that's the requesting semaphore. That's pretty straightforward. Releasing semaphore. Increment the, well, deallocate one. That the process was requesting. So the process will request a CD, and a process will release. I got these extra. Sorry. Yeah, something like that. Request what? Well, request a CD. Release a CD. So each of these is part of the semaphore. Releasing deallocates one of them. Okay, that's part of it. The one that's coming in, this guy, this CD guy. And then it's going to increment the number of CDs. And the most important thing is it signals the CD queue. Okay. Now, what happens at the CD queue is on a signal is the same thing as if it's requesting. So what's going to trigger is it was sitting there waiting on the queue. And what we're going to do is we're going to bring it right back in for that process. So we're going to bring the process back in. So this is really going to be a recursive call on this signal. It's going to be get that wait guy past the process ID, right? Process ID to this queue so that it will release it from the queue. So maybe what you should do is do it this way. Let me do it another way. Why don't we have a signal event? Okay, on a signal, it basically does this. Removes, and it's pretty first come, first serve, I guess. Removes first process ID from CDQ. Okay? Because remember, it could keep decrementing, right? We could keep decrementing this number here. But it looks like I'm not really doing this here. If it's less than 0, I don't decrement. I guess you could. Removes the first. Let's see what I say. Removes first process ID from queue, and then does this requesting with this process ID. And that basically invokes the process of this requesting semaphore. And that should handle the semaphore pretty well. And that's most of them. Most of them work very similarly. They have a request component, a release component, a counting variable component, and a wait queue that goes with that. Is that better for you? Is that clear without putting all the code? Okay. Because that's really what they are. Okay, and the idea is you could keep requesting and they keep getting placed on this wait queue, and what you're doing is you're not in a spin lock situation. But I'm going to tell you that to implement the semaphore, this queue could be shared, right, as a shared data structure. And I have a bunch of questions on the test regarding shared data. So you really need to understand that concept of shared data, that you really need to lock and protect. So when this requesting semaphore is putting it on the queue, this queue, it has to lock that queue. It has to do it has to be in a critical section, even though this whole thing could be in a critical section as well, right? This particular process could be, or this particular semaphore could have had a lock on it. If that's the case, then we're okay. But if we don't have a lock on the semaphore, then we'll have to put a lock on the data that we're touching. Okay, anytime we touch these data, like this data, we'd have to lock that before we make a change, and lock that before we make a change. Or we lock the whole semaphore. There's got to be a way of securing this shared data. Because this guy is using it, and this guy is using it, and this guy is using it. Well, this guy is using it, just this guy is using it. So this one's adding it, this one's subtracting. It could be two different processes on semaphores. I hope that's clear, right? I know it's kind of hard to think in asynchronous terms, but that's what it is you want to synchronize things happening to shared data. You want to synchronize so that you know that you're not in any kind of a race condition on this data. But you don't want to lock it for a long time. You know, with a lot of spin locks, you don't want to. That takes time, and it's just busy waiting. So you kind of invent this concept. So you might have a small spin lock that'll let you in on the semaphore. Okay, so that you're the only one, and that secures the data. And then you release that lock. So these things are going to be pretty quick in terms of actually executing. It's pretty fast. So it's just how you lock them. And I mentioned a while ago when we went through the chapter 5, this came up in 5 or 6. I can't remember which one. That some processors now are having code for semaphores so that you can do it atomically as an instruction that's uninterruptible. So that's pretty cool. Okay, any other questions? Good question, Megan. Okay then, I'm going to say that's going to be it for tonight. Thank you all for participating. You have a great evening, and I'll see you on Thursday. We'll do the review, and it should be a short evening on Thursday. It shouldn't take a lot of time. But I'm going to review everything that's on the test. Thank you guys. I appreciate your participation a lot.